What's up, guys? Hey Devs, back in for another LeetCode problem. Now, I have recorded this twice now, and my explanation is kind of lackluster, I'm not gonna lie. I kind of get confused on, not confused, it's hard to explain the thought process behind this one, but we'll kind of go right into it. We're doing problem 35, search insert position. Given a sorted array of distinct integers and a target value, return the index if the target is found, and if not, return the index where it would be if it was inserted in order. So the first thing we want to do is we want to try to find the target, and the easiest way to do that, and another thing we have to do is you must write an algorithm with a log n runtime complexity. So that means we can't just do a for loop over each element, and then return it if we find it, and if we don't find it, if the next, we could do for int I is equal to 0, I is less than nums. I'll just go and type it up. We could do for int I is equal to 0, I is less than nums dot length, and then I plus plus. We could do something like this, and then check int is equal to int check, or we could see if the if nums dot length, not nums, if nums of I is equal to target, then we can return the index value of I, right? Return I, and then else if the target, or nums I is greater than target. That's saying that because if we haven't found the index where target's supposed to be, then it should be less than the target. But if the number held at I is greater than the target, then we know that it should be inserted at that position, and everything to the right should be scooted over, right? So then we could return I. Return I. We could see. Oh, I'm gonna do an equal to. And then we do an else, because the compiler knows that it's smarter than us, we can return I, or we could just return the nums length at the end. And this would be a naive solution, or not, this would be an ON solution. Nums dot length. And all this is saying is we're looking for the number. If the number is found, then we return the index of the number, right? And then else if the number that we found, or the number we're looking at, is greater than the target, then we know we passed the position it should be at. Not passed, we know that it should be inserted at that position, and then everything after it should be moved over. And then if none of that is true and it breaks out of the for statement, then we know it should be inserted at the end of the list. And this should give us correct solutions. Yeah, accepted. And then if we go ahead and submit this, I wonder if it will, yeah. But this is an ON time complexity, because worst case scenario, we have to check every value and then return the nums length. And we don't want to do that. So one thing you can do, these are my solutions. That's a bad solution. That's called what's the searching algorithm? I can't think of the searching algorithm right now. That's just like you check every value individually until the end, and that has an O in time complexity, which is very long. There's a way to do it. Since it is a sorted array of numbers, we can do a log n time complexity. And this can be accomplished using binary search. And the way binary search works is, given the array of numbers here, we set a left value, and we set a right value, and then we want to check the midpoint, which would be 3 in this scenario. And then if the target is equal to 3, we want to return the index that 3 is at. And then if the target is less than 3, we want to move the high index value to the 3. And then now we're checking, or to the 3 minus 1, now we're checking the subset of the array. So each pass, you will split the array in half. You'll check the either the left or the right side of the midpoint, and then we'll be looking at that subset, and then you'll check the midpoint of that subset, and then get another subset, and then over time you're splitting the array in half and half and half. So the probably the best way to do this is just this simple algorithm. If you search a binary search algorithm, this would be the algorithm you get. So int high is equal to nums.length, and nums.length gives us the amount of elements in the array. We want the last index, so you do nums length minus 1, and then int of low is equal to 0, and then you can do while low is less than or equal to high. This is saying that because at each pass we're moving one to the midpoint, and then we're moving the other to the midpoint, plus 1 or minus 1, right? So this is saying that the indexes have passed each other, and we're no longer looking at a subset. We've passed each other, and then and if they pass each other, that means the target is not inside of the array. So we will go ahead and we'll go ahead and find the midpoint. That's what we want to do for each pass. So the mid is equal to low plus high minus low divided by 2. And no matter what the high and low is, the subset of the array. So if low, in this case, if for 7, high is 3 and low would be 0. After the first pass, the midpoint would be 3. Since 3 is not the value, and then 7 is greater than 3, we want to move the low index value to 3 plus 1. So that would give us the index value of 2. So low would be 2 and high would be 3. And then once again we would compute the midpoint. So that would be 4, or 3 minus 2 is 1. 1 divided by 2 is 0.5. It's integer division, so you would get 0, and 0 plus 2. So the midpoint is now 2. We would check the value of 5. 5 does not equal 7, so we know that it's not in 5, and it's not in the left side of 5, and it's not from the low point to the midpoint, right? So what we want to do is we want to take the low, we want to move it to the midpoint plus 1, and that would give us low and high is equal to 6. We check to see if 6 is equal to 7. It's not, so then we want to go ahead and see if 6 is greater than 7 or less than 7, and we see that 6 is less than 7. So then we would go ahead and move low to the midpoint plus 1, and then low would try to find the next, would give us the subset. Well, at the end, low would end up being our index value. That's what I'm kind of hard to explain, is that intuition. But the binary search algorithm kind of goes like this. You can search this up in any programming language, and probably search up a better video to explain it. But if nums at mid is equal to target, then we want to return mid. So this is saying that the nums at the mid index is equal to the target. We found the target, so we return the index of the target. That's what the first part of the question founds. And then this is the logic for, well, actually, we don't even need that. I could just do that. So then we want to check else if nums of mid is greater than the target. And if the number is greater than the target, then we want to move the high pointer down to mid minus 1. So high is equal to mid minus 1. And then else, if, so we checked if it's equal, we checked if it's greater, so else it has to be less than, right? So then we want to move the low pointer equal to mid plus 1. Plus 1. So that goes ahead and it gives us, returns us the index if the target is found using binary search. But also using binary search, it shrinks it down to the, so in the case of 2, the final value to be checked would be 1, or the index value of 0. So mid would be 0, high would be 0, and low would be 0. And what it does, because 3, it checked 3 already, it knows 3 is not the value, so it goes less than. And then it checks the subset of 1, it sees that 1 is actually less than 2, so it knows to put low plus 1. But we already checked 3, and we know 3 is already there, and 3 is actually greater than our value. So low, once it breaks out of the loop, for this specific example, high would be 1, mid would be 1, and then low would be equal to 2. Or, I said that wrong. High would be 0, mid would be 0, and then a low would be set to 1. So what that's saying is that low will always end up being the index value we want to return. Return low. And then when we go ahead and check that in the test results, we can see that it runs for all 3 of the sample cases they give us. And then if we go ahead and submit that, there it goes. Oh, I remember it's a linear search. You just go straight through the line. So the 2 submissions we showed was linear search, but this has an O(n) time complexity, and it asks for n log n time complexity. And well, where did that go? And in order to achieve log n time complexity, we want to this is splitting the array each time. So we would end up getting it majority of the time. Not majority of the time, we get it every time. But this one was a hard one to explain. I don't really know how to explain binary search. But hope y'all enjoy. Y'all stay blessed. Enjoy the next episode, and bye.